Hi everyone, my name's Will Lord. I'm a product manager in Arm's AI and Developer Platforms group. As a team, our mission is to enable application and AI developers to build their best experiences on any Arm device, from laptops to mobile phones, cars to cloud, and smart factories to home assistants. I'm delighted to have been asked to join you today to talk about how we can work together to make WebAI on our architecture a reality. But before I do, I wanted to briefly introduce you to Arm, creators of the most pervasive compute platform in the world, and our unique position in the AI revolution.
The future can feel impossible, but we build it together, one beat at a time. Technology helps us do impossible things, like detect cancer cells earlier than ever before, help students learn about the world, and map brand new ones. Arm's technology is helping defy expectations, and it's leading the way to keep us all safe. Arm is in billions of devices all over the world, unleashing the power of AI, helping us do the impossible. Because impossible is technology waiting to happen.
So, if you know Arm, you probably know us as the dominant force in the smartphone market, where 99% of handsets are built on top of the Arm architecture, including devices from Apple, Google, Samsung, Xiaomi, you name it. Or perhaps you run all or part of your cloud infrastructure on AWS Graviton, Google Axion, or Azure Cobalt servers, all built on Arm in a segment where, for the first time this year, 50% of all new compute capacity added by hyperscalers was Arm-based. We've got over 325 billion Arm chips shipped, and we now touch the lives of every single connected person in the world, all enabled by a growing software development community who write code on and for the Arm-based architecture. Our product portfolio includes CPU, GPU, and NPU designs, each with features designed specifically for ML and AI workloads. On CPU, our long-standing Neon matrix multiplication algorithm has been joined by SVE2, which added vector support, and most recently by SME2, which added multi-vector ops, and in combination with our Clyde AI integrations, has given up to 5 times AI workload performance uplift when compared to previous generations. If you've got an iPhone 16 or later, or you're using an M4-based Mac, you're already getting the benefit of SME2, and Android devices are just around the corner. In the GPU space, we've got a long history of delivering exceptional gaming and graphics performance on mobile through our Mali and Immortalis product lines. And in August, we announced our new Neural Accelerator technology, or NX, an IP block designed for optimum performance of AI and neural graphics workloads running on GPU that will be available in 2026. And finally, our line of Ethos NPUs have brought ML right to the very edge, allowing AI integration into IoT devices and heterogeneous systems. But as you all know, hardware is really just a vehicle for software. And that's why we invest so heavily in developer experience and enablement. Web applications and the supporting technology behind them have always been important to Arm, whether they run in the browser or natively in an operating system like Android. We even added a JavaScript data type conversion instruction to our architecture back in 2016. You can probably imagine that adding instructions for individual high-level languages is pretty unusual, but that's just how central JavaScript has always been to developer and therefore Arm's success with the web. So let's now take a quick look at what we've been doing in two areas that I think are particularly relevant to WebAI. A lot of things on-device inference, and then on web APIs, libraries, and frameworks. So a lot of people have been talking about this, and we've seen concerns around cost, privacy, and latency of cloud inference growing. And along with that, we've seen end-user expectations of device capabilities growing, especially when it comes to AI. And we've responded to those twin challenges by developing Kleidi AI and the Arm Kleidi libraries, a set of optimizations for Arm CPUs that leverage features like SVE and SME for maximum AI performance. The great news for developers is that these libraries are integrated directly into the most popular AI and ML frameworks and runtimes, including PyTorch, Executorch, ONNX, MediaPipe, LiteRT. And the great news for consumers is that unlike GPU or NPU, everyone's got a CPU to run these applications on. In our demonstrations of stable diffusion, speech recognition, chat, and audio generation, we've seen local model performance increases of between 2 and 6x when running on Arm v9 devices. For example, Phi 3 running on a Windows on Arm PC shows 2.4x faster prompt processing, while on a flagship Vivo X200, the uplift is 2.6x, thanks to the Kleidi integration with ONNX runtime. For WebAI, we think this is potentially huge news. If we can connect the browser to Kleidi through the right combination of on-device ML frameworks and web APIs, web developers should be able to get similar performance uplifts without lifting a finger. Meanwhile, in GPU land, we're taking steps to make both graphics and general-purpose neural networks more performant than ever. With our recently released ML extensions for Vulkan, we've introduced native support for tensors and graphs, making ML a first-class citizen in what's generally seen as more of a graphics API. We've seen a lot of enthusiasm from mobile companies for our first demonstration of that technology, a highly efficient neural upscaler that can halve GPU workload while rendering at 1080p from 540. There's definitely a lot of potential for browser integrations, both for games and non-games use cases, which we'll talk about a little later on. So let's now turn to some of our work on emerging and foundational web technologies. So we're a pretty recent entrant to the GPU for the web working group at the W3C, but our team have been working extensively on WebGPU for the last few years, making many contributions to Dawn, the WebGPU implementation used by Chrome, with a particular focus on native usage with Vulkan. More recently, we've been working directly with Google on WebGPU performance improvements in the new ML framework ML Drift, and on tooling support to make it easier to debug and optimize WebGPU graphics in the browser. On the WebAssembly side, we've got a dedicated team working on V8, the WASM engine used in Chrome and Node.js, which gives us the quickest route to optimal performance across billions of Arm CPUs. We've made hundreds of patches to V8 with a large number of recent changes focused on memory optimizations. And as the WASM spec has extended to cover memory 64, scroll the notes. Thanks. We've been ensuring that larger models and other memory-intensive applications continue to run optimally on Arm. We've also developed a WASM benchmark that we'll be making publicly available soon, making it easier for the industry as a whole to understand where bottlenecks and performance gaps exist so that we can work together to resolve them. Also worth calling out that we spent a lot of time and energy on LLVM, which is really the kind of de facto compiler for WebAssembly and the WebAssembly runtimes. That's a project where we've made over 14,000 patches, all of which have a downstream impact on the performance of WebAssembly. So, web technologies have played a huge part in the growth of the mobile market over the last 15 years. Obviously, they're foundational to the mobile web, but web views remain a fundamental part of many native apps, and browser technology appears in many parts of mobile operating systems far beyond the standard web browsing experience. Our big success in mobile has been driven partly by our investments in those web technologies and software support for them, particularly with Chrome and Chromium. Like with WebAssembly, we've got dedicated teams who are focused on ensuring that Chromium-based browsers are secure and performant on ARM-based hardware, whether the underlying OS is Linux, Mac, Windows, iOS, or Android. And that work extends beyond today's hardware to future hardware features. Our teams are often working on hardware that won't be available in the hands of consumers for 3 or 4 years, meaning that when new devices are in your customers' hands, you can be confident that your apps will be running the best possible browser experience. So at this point, you might be thinking, so what? We've demonstrated ARM's commitment to maximizing on-device AI performance, and we've seen ARM's significant and ongoing investment in web technologies. But this is a WebAI summit with a focus on local AI inside the browser. So how can we give web app developers the same kind of experience that we're able to give native app developers targeting the ARM hardware? Well, if we want to do that and give web developers the most direct way to access our hardware ML accelerators, whether that's on mobile or desktop, that means connecting up the browser to the right acceleration libraries and APIs. So let's imagine just one way we could do this. Let's say you've got a JavaScript app that uses ONNX runtime web. As a developer, you don't want to worry about what hardware is available to your customer when they run that app. And that kind of device abstraction is exactly what WebNN is designed for. You just write your amazing app, and it auto-magically runs on every single device, whether that's CPU, GPU, or NPU. And to get you the best performance on ARM hardware through WebNN, we need to provide you with 2 things. First, a GPU path using a WebNN backend wired to our Vulkan ML extension's data graph pipeline. That would route to shader cores today and to neural accelerators on upcoming ARM GPUs without your code changing. It's going to be great for CNNs, transformers, camera and video use cases. Secondly, you want a CPU path, which we'd likely achieve by wiring WebNN to XNMPAC, and from there to Clyde AI. Great for bursty workloads and providing a fallback when GPU isn't present, busy, or not performant for your use case. If you wanted to be deterministic about running on the GPU, you could still continue to bind a GPU device to WebNN or go straight through WebGPU for more granular control. The great news is that Clyde AI support is already baked into XNMPAC, so you can get some of this if you're using LiteRT WebNN backend in Chromium. But the bad news is obviously twofold. First of all, as we've been hearing, WebNN isn't widely supported in every browser today. And second, it charts a pretty narrow path to WebAI acceleration on ARM, with only a limited number of device types and platforms supported. So there's work to do, and we've been thinking about how we can choose the right path. And one of the ways we think we can do this and drive continuous improvements on the paths that we pick is through the thing that all hardware companies love, benchmarks. If you want to understand which combinations of web APIs, browser integrations, and hardware availability perform best in the real world, then a benchmark suite similar to or built on top of Speedometer would be a great place to start. Imagine if we tested not just for browsing, text input, and to-do creation, but also for image generation, object detection, or chatbot tasks. These are just a few of our ideas for now, but what we really want to do is hear from you. If you're an application developer, come and talk to us today. Tell us about your big challenges. Maybe it's memory management in WebAssembly, or you want better insight into WebGPU behavior direct from DevTools in Chrome. Or do you want to add AI features to your next in-browser game? Whatever it is, we want to hear about it. We've got a whole team at Arm who can support integrations, migrations, and optimizations in partnership with you and your team. There's quite a few of us here today, so come and find us over by the demo station. And you can also take a look at some of the technologies that I discussed on our learning paths or on developer.arm.com. I'd also encourage you to sign up to the Arm Developer Program, where you can get latest news and direct support from some of our engineers and our ambassadors, like Gordon, who's here today talking about Bangle.js, which runs on a very cool little watch that is ARM-based. So thanks so much for listening today. A huge thank you to Jason and the rest of the organizing team for putting together such an inspiring lineup. I look forward to working with some of you to build the future of WebAI on Arm together. Thank you.